Evening. This is Professor Kingling 2. Now you want me to give the talk because I'm supposed to be the third one. On schedule, Professor Uchida, will he give the talk? Or you want me to give the talk now? Can you hear me? Can you hear me?
As I understood, she do want you to give the talk now because the Uchida is not could not connect it.
Yes, sir. I would like you to present your topic. So we are ready to hear your speech. Thank you.
No problem. Okay. I will be happy to give my talk now. Okay. Yes. Good evening. I'm in Hong Kong. These are now 8 o'clock. 7 o'clock. The title of my talk is shown here. Reliability Challenges in Mobile Technology for Big Data Era. With City University Hong Kong, Department Material Science Engineering, and Department of Electrical Engineering. For my talk, I will give the introduction and definition of reliability failure, okay, definition of failure, and then most important failure mode is due to electromigration. Now, key of my talk is number 4, modified mean time to failure equations. Yeah, because we have new equation to present the failure. Yeah, finally the summary, okay. Our silicon device, the current voltage device, the current density can reach 10 to the 6 M per centimeter square, very high. Okay. At home, in the lab, the electricity in the wire is only 10 to the 2. Okay, so these are 4 order of magnitude higher in device. Because of high current density, therefore, electromigration occurs, which lead to void formation. Therefore, the circuit will open and fail. It is a time-dependent event because it takes time to do so. So it's a reliability problem. A device fail around its mean time to failure. Okay, it should fail. Okay, then it's a normal failure. Okay, no problem. But failure before mean time to failure, then it is an early failure, which is unacceptable. We must avoid that. Okay, so we emphasize so-called early failure. Okay, you fail before you should. Now, a mean time to failure. Mean time to failure is defined as the normal lifetime of a device in service. Okay. Consumer electronic product fail to be used in the field consumer. Okay. Yeah. To project future application of existing device where the applied current density may increase. The second purpose of mean time to failure, because if a company has a very good device doing very well, they want to see if it can be used in the future, second generation, third generation. But no doubt because of function, function increase if applied current density will increase. However, these may cause faster failure. Then we like to know how many more years can be used if we current density. Okay. Particularly in my talk, we shall consider mean time of failure of electromigration, because this is a major damage failure in electronic device. So you ask, what is electromigration? It is atomic motion driven by electrical force. Atomic motion driven by electrical force due to scattering of atom by high density of electron. The diffusion of the atom will be enhanced in the electron's direction. Please know this electron direction, not electric direction. Vacancy will move in the opposite direction because this is a CC metal. Okay, the diffusion mechanism is by vacancy. So atom moves to the right, vacancy moves to the left. But vacancy condensation will cause a void formation and open circuit. The accumulation vacancy in the cathode end will form a void, okay, a void, which will lead to open circuit. So this is the problem. Let me quickly explain the basic of electromigration. It is atomic diffusion driven by electrical force, F. Define F equal to Z star E. Small E is charge, capital E is field, electric field. Z is defined effective charge number of the atom. So small e electric charge, rho resistivity, J is current density. Okay, because rho J. Okay, so yeah, the schematic diagram shows that we have atom, say the shaded atom, although want to exchange position with the vacancy. Okay, it is enhanced by the electrical force. However, it has to squeeze through window, given here by 4 atoms here. Okay, so now when the diffusion atom is activated state, you can see it's pushing the atom open. Okay, therefore the scattering of a group atom at this stage is at least 10 times higher than normal atom. So that's why these electrical force is very big. Okay. Now, it will be easy to understand if I can tell you the physical meaning of Z star EE. Okay, this effective charge. What does that mean? In double E, we know that the meaning of electrical field E is that if we place a charge of E in the field, you place a charge E in the field of E, the charge will feel a force EE to move it. So these are the force, electrical force on the charge due to the field, electric field. In the field, say in the field E, and we assume that the atom will feel a force of Z star E, Z star E times E to move in the E direction. So this is a big charge, okay? Z star E. Find Z star to be the effective charge number of the atom. It's about 10 times that of the valence electron number. Okay, like copper, valence electron is 1, so effect charge is about 10. Aluminum valence atomic electron number is 3. So Z star for aluminum is 30. Okay. All these has been experimentally verified. All right. So let's show some failure. Okay. First, electromigration aluminum short strike on titanium nitride. This is a PhD thesis in Stuttgart, Germany. Okay, 1999. Yeah, this is a line deposit on titanium nitride, and then they cut short. Okay, short section, and then they pass current. Okay, from the lower bottom to the upper, and then you can see, you know, the damage. Okay, here's the bigger picture. You see the voids forming in the cathode, and the HELOC, due to conservation mass, HELOC is pushing up in the anode. Okay, this under current 10 to 6 m/centimeter square, temperature 225 degrees C. Okay, so very clear. We can observe electromigration damage, okay, by using these kind of so-called. Okay, all right. Next is copper, because 20 years ago, the aluminum metallurgy interconnect is replaced by copper. This image is a little bit vague because it's taken through a glass. Now, at 100 degrees C, the by temperature, diffusion copper occur on surface. So the current going left to right, vacancy come back, vacancy come to this end, accumulate and form the wall. Okay. The surface diffusion, so these cathode end getting thinner and thinner, right? Thinner. So current density gets higher. So electromigration is faster. Okay. On the other hand, if your structure is then because this contact point is very small, so when electron push atom away, vacancy come back. So you quickly form a void here. Then this is an open circuit. So this is if you have such structure, it fails very quickly. Now, third kind of failures in the solder joint. Okay, featured solder joint. Here's a daisy chain. Yeah, from bomb 6, 5, 4, 3, 2, 1. Very interestingly, on bomb 3, bomb 1, when electron get in the solder joint, and then there's a pancake-type void. Okay, pancake-type void. Okay, occur here. Yeah. Electron cannot go through the gap. Okay, so therefore electron will come to the front push atom down. Vacancy come back, fit the void, so the void will grow laterally. Therefore, if this void, pancake void, if go across contact, circuit will fail. All right, circuit will fail. And very unique. Very unique. Okay, you only form at 5, 3, 1. All right. Then we go to synchrotron radiation. Take tomography, image chemical void. See on the top, the voice here. On the side view, the voice here. All right, so very clear. Okay. Yeah. And to define the mean time to failure. Okay, I must say, Professor Black, okay, he gave an empirical equation. Yeah, and mean time to failure defined by J minus N exponential EKT, okay? There's no negative at EN. J power N, and he that N should be 2. Because empirically, experimentally, he found it always 2, okay? But theoretically, it has been a controversial point because we've just assumed kinetic theory of void formation due to vacancy diffusion, N should be 1, but it should be 2. Okay, so this is a big issue, okay, for a long time. Therefore, we want to understand more, okay? Now, the Planck equation has 3 parameters, the prefactor, the J exponential acquisition energy. We have known. So typically, we need to perform 3 temperature, 3 current density. We call 3T, 3J. Yeah, this is takes a big effort. It's a challenge how to reduce it. Okay. Now we come to the modified equation based on entropy production. We follow on saga, find a pair force and flux, okay, conjugated force and flux. He said the product of X and J, Jx, must equal to so-called production, TTS entropy production. It's a volume, okay, it's a per volume, okay. We will show these below, okay. For example, we consider electrical conduction, pass a current, density J, through this conductor from X to X plus dx. Number charge is JADT because J is defined as number of electrons per centimeter square per second. The voltage drop defined. If current resistance will cause a voltage drop, you'll go from X to X plus dx, okay. Drops defined. Then we go back to first law of thermodynamics. Okay, this is well known. Then we push this term to the other side, we get TDS equal to that. We consider each conduction of pure metal under constant temperature, constant pressure, then we don't have the last 2 terms. We only have TDS equal DU. D is the internal energy, internal electrical energy. Now, energy, simple, because the unit is called EV, right? EV, unit of energy, EV, is charge times voltage. Therefore, what is the charge? Charge, number charge is JAT, right? JAT, number of electron per unit area per unit time. So this JAT, the voltage drop. And we put d phi equal to phi x minus phi x plus dx. Okay, so these phi x into phi x plus dx. Okay, then very simple calculus. We just divide this by dx. Okay, dx. Okay, and then we multiply x up here. Then because A times dx is volume V. Okay, so we change that J V dt. First derivative diffuse dx. Okay, now dx is electric field. Okay, so we obtain on Saga equation. So this entropy production equal to flux times driving force. Okay, for this Joule heating, you remember that? Okay, this equal Joule heating. Okay, rate of energy change, okay, is pi square r. It's just this term times volume, okay. It's straightforward, okay. Prove that. Then it means that low power device means low entropy production device, okay. EE always talk about low power device, but what it means physically is low entropy production device, okay. So we now use this equation to derive the mean time to failure, okay. Then we put this electromigration JE, we put T over here, we integrate T to failure, and then S threshold, okay. Then we define these to failure, mean time failure, then we move this term below here, we got that, okay. Relay is J minus 2, okay. Yeah. More specifically, I'm not going to go through this with you. Then this max, the driving force, need A minus 2. So back, even though he gave the empirical question, but he's correct. The current density dependence square, okay, but should be T over J squared, not 1 over J squared or nor 1 over J, okay. Then by the same principle to thermal migration, okay, this is another very important mode in failure. Sure. Oh my God, this is not available before, okay. And then for stress migration, okay, yeah, this is the same thing, yeah. Here, and then we obtain a new so-called equation for mean time to failure due to stress migration, okay. Now, typically in thermodynamics, we ask Gibbs free energy change. We do not ask entropy change, okay? How come? Yeah. However, you know dG equal dH minus Tn, enthalpy, okay. On the other hand, if we have an ideal system, what does that mean? It means that EAA equal to EBB equal to EAB, no chemical effect, okay? No chemical effect, dH is 0. Therefore, dG is equal to entropy production in the ideal system is free energy change. Yeah. So, like copper, we consider today copper. Copper is ideal condition. So therefore, will apply. Okay. Therefore, let me make my summary. Yeah. Joule heat of major concern in mobile technology. Yeah. In big issue, we need low power or low entropy production device. Entropy production is the theoretical base in obtaining the mean time to failure equation. Verifies that the empirical finding at J2 dependence is correct. Okay, so J should be square. Okay. Also, we obtain equation for electromigration, thermal migration, stress migration are now available, as well as any irreversible process, provided that if the driving force and the flux are known, that we can obtain mean time to failure equation. Thank you. I finished my talk. Thank you for your attention. Yeah. Any question? I'd be happy to try to answer. Yeah.
Yeah, thank you, Dr. King, for your wonderful speech. So,